Good morning, ma'am.
Many students have not joined. What's the problem? Okay, so let's start the recording also. So those who will not join, they can.
Ma'am, the NCC parade is over now.
Yes, yes, yes. Okay, so we were discussing about the half-wave rectifier and we are deriving certain parameters. So in the previous class, we have derived various parameters like your DC voltage, DC current, then RMS voltage, RMS current, then yeah, so RMS, VRMS, IRMS, IDC, VDC, then efficiency of the rectifier. So as we have seen here, only 40% efficiency we are getting here. Peak inverse voltage, then form factor, ripple factor. Yeah, up to
Ma'am,
this
can you
much.
explain PIV again?
Peak inverse voltage, no? Okay. So actually peak inverse voltage means it is the voltage in the reverse bias condition. If you are applying the reverse bias voltage to a particular diode, then up to how much maximum voltage we can apply to that diode, because you know from the VI characteristics, if you are applying the reverse bias voltage, so in that case it is entering into the reverse direction, and initially the current will be very small amount of or negligible amount of current we will get. Okay, after that it enters into the breakdown region by producing a huge amount of current. Okay, so if this is the current axis and this is the voltage axis, so if even if the whatever the voltage will increase, voltage will be very constant but current will be increasing very rapidly. So in that case, for a normal PN junction diode, the reverse voltage, this high amount of current is not suitable, or the diode cannot withstand that amount of current. So obviously current is increasing means power drop also very higher. P is equal to V into I. So the diode get damaged. So we have to know that up to what is the maximum limit or maximum reverse voltage we can apply to the diode. so that according to the capacity of the diode we can apply the input voltage. Like when we are applying the input signal, the input signal means this is, if it is plus bm, this is minus bm, minus bm also we are applying, so it is the alternating current or alternating voltage. So if you don't know what is the maximum limit of that diode, and if you are applying a higher voltage, in that case, if it exceeds the this bm value is very higher, then in that case the diode get damaged. So this PIV rating of the diode should be known. So uh, how this peak inverse voltage is determined? So in the reverse bias condition, like in the rectifier, if it is the half wave rectifier, so in the reverse bias condition, what is the voltage drop across the diode? That is your, that will give you the information what will be the possibility of maximum voltage that will appear across the diode if you are applying a particular signal, like whatever the input you have given, and here what is the input we are getting. So what is the rate of the, according to the value of this input voltage, we should determine what is the maximum possible voltage across this open terminal. So this voltage will give you the peak inverse voltage. So in the, suppose in the negative half cycle, that is the reverse bias condition, this will be minus plus Vi, okay, and this is the, let's say, peak inverse voltage. Let's say this is your negative to positive. This is the PIV voltage, or this PIV rating, VPIV. Let's say, we can say. So we can, if you apply the KVL here the voltage, output voltage is 0 now. So if you apply the KVL here, so this will be positive to negative, minus of VI, plus negative to positive, plus peak inverse voltage, that is 0. So is this PIV will be equal to, actually VI means that is the maximum limit we are calculating, the peak inverse voltage. So we are not taking the VI, rather we will take it is VM, the peak of the voltage. So this is plus, yeah, PIV is equal to plus VM. That means maximum VM amount of voltage will appear across this open terminal. So whatever the diode we will choose, the diode must have a PIV rating which is greater than equal to VM, so that whatever the input signal we are considering, like suppose we are considering the input signal plus minus 5 volts, peak value will be 5 volt. In that case, the diode which we will choose, its PIV rating should be greater than 5 volt, so that safely the diode can be used for this particular circuit. So that's why the PIV rating or the peak inverse voltage, what is the possibility of in maximum reverse voltage appear this open terminal, that should be determined. So it will vary from circuit to circuit. So here only VM amount is required. Okay. So when we consider the full wave rectifier, then we can just full wave rectifier, the PIV will be changed. So we will calculate that. Okay. So this is about the peak inverse voltage. Are you clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. So I think two more parameters are there in your half-wave rectifier analysis. Once you done the derivation for all these parameters for either of the rectifier, like half-wave rectifier or full-wave rectifier, other one is just a little little variation is there. You can easily do it. Like for the full-wave rectifier circuit, only the difference, little difference is there. Whatever the difference I will say. Let us first of all complete this half-wave rectifier. So just that is, it seems to be a very larger content, while actually it is content is very small. Concept is same. The same process you have to follow. The value will be little bit vary. Okay. So one more parameter is your transformer utilization factor. Transformer utilization factor. It is called as TUF, transformer utilization factor. So this transformer utilization factor, basically in the designing process, designing any power supply of the rating, wherever the transformer is used, the transformer is to be properly, it should be chosen, okay, so that it can be utilized whatever the efficiency of the transformer should be properly utilized. So we have to choose a proper transformer. So this transformer utilization factor is used for the rating of the transformer. It is also used for the rating of the transformer, how the transformer quality is. Okay. So the TUF, it basically it is calculated like this. This TUF with reference to the secondary winding, if you are calculating, then DC power supply, DC power delivered to the load divided by AC power rating of the transformer secondary winding. Okay, for the transformer secondary, it is the whatever the AC power that we have to calculate. So for DC power delivered to the load, the DC power delivered through the load means obviously it is IDC square into RL, that is the DC power delivered to the load. In the load resistance is RL, whatever the IDC we are calculating, according to that the DC power will be calculated. And what will be the AC power rating of the transformer? So this will be VRMS into IRMS. So this VRMS will be actually this VRMS, what is the actually whatever the VRMS we have calculated, that is the after transforming the AC load to the uh, after AC, whatever the pulsating DC that we are calculating, that RMS we are calculating. So that is the whatever the value BM by 2 we are calculating. That value is the pulsating DC, or for this signal we are calculating the RMS. But this VRMS, this is basically in the beginning of the transformer secondary winding, like if it is a second transformer, so at this point what is the VRMS that is required? VRMS at the secondary. Okay, so this voltage current will be same,
BM by root 2.
yeah, BM by root 2. So how it comes BM by root 2? Can anybody justify? Earlier whatever we have calculated, in that case we are getting the RMS value how much? BM by
2.
BM by 2. But here
It is
why this?
overall from pi to 2 pi.
Yeah, actually in the secondary winding the waveform is like this. Okay, the waveform will be like this. So 0 to pi, pi to 2 pi. So earlier when for this case when we are calculating from pi to 2 pi, we are considering this is 0. But here from pi to 2 pi the value will be minus sin omega t. Okay, so that is the difference when we are integrating this and taking the RMS value like 1 by 2 pi, 0 to 2 pi root over, this is Vm sine omega t square d omega t. This calculation here we have to consider, it is 1 by 2 pi. Here you have to consider 0 to pi as Vm sine omega t plus pi to 2 pi when we consider it is minus of Vm sine omega t. In this way you have to integrate. So you just, if you evaluate this integration, then we will get this Vm by root 2. So usually for the sinusoidal signal, you know that when you calculate the
Ma'am, the screen is not visible.
screen is not visible for all
Visible, ma'am.
students.
Visible it will be.
Ma'am, it's visible.
So you might have problem from your side, just check. Okay. So for normally for sinusoidal waveform, it is Vm by root to the RMS value. So if you put this value to this here this condition, so this will be IDC square into RL. So this is Vm by root 2 into this is Im by 2. Okay. So this for this if you simplify this, just simplify it, what we were getting, and IDC value is your Im by pi this square into RL, and this will be Vm into Im by 2 root 2. So you just simplify it, so what we are getting, so this will be 2 root 2 by pi, and this will be IMRL, and here it is also IM is also there. So this will be IM. One IM get cancel out, so 1 IM RL divided by BM can also be, it is written as your IM into RL, so it is simply this will be simply your 2 root 2 by pi.
IRMS pulsating DC.
Yes,
That IRMS is of pulsating DC voltage.
which one?
In that equation, in denominator VRMS into IRMS, so IRMS is of AC component
Yeah,
or
current, whatever the current will be same. Okay, same current is flowing through this loop, na? There is no
okay.
change in current.
Okay.
Okay, so this will be, I think it is pi square, na? Pi square. 2 root 2 by pi square. So if you calculate this value, it is coming 0.287. That means the transformer utilization factor is 28.7%. So whatever the efficiency of the transformer, it's only the 28.7% of the transformer efficiency is utilized for this rectification purpose. So this is showing the poor performance of half wave rectifier. We are getting the efficiency less than 50%, that is 40.2%. We are getting the ripple factor, that is 1.21. That means a lots of AC component is there, and transformer utilization factor means only 28.7% of the transformer power is utilized here. So this shows the how the efficiency or how the half-wave rectifier is behaving very poorly. So that's why the half-wave rectifier is hardly used for rectification purpose. So we need to increase the efficiency or the performance of the rectifier. So we will use the full-wave rectifier circuit. And one more parameter is that is the voltage regulation. Voltage regulation. So actually this voltage regulation is the variation of the DC output voltage as a function of the DC current. So this percentage regulation is denoted as voltage in no load condition minus voltage in full load condition divided by voltage full load into 100% if you are calculating in percentage. So in the load condition, in the no load voltage or the V no load, this voltage will be simply your Vm by pi, that is the DC voltage, and V with full load. If you are considering the full load, in that case this voltage will be, this will be Vm by pi, which is no load voltage, minus whatever the voltage if you are considering a fully loaded condition. In that case there will be current into your the source resistance plus your forward resistance of the diode. If you are considering this resistance, then some voltage will be dropped across this, so the full load voltage will be just less voltage from your no load voltage. So this is the value. So if you put this to value and calculate this percentage regulation, this will be simply you just put the value, this will be Vm by pi, or we are not giving so much time, so you just put this value. So this value will this value, all the values just put, we are getting this IDC into RS plus RF Vm by pi minus IDC into this RS plus RF. You simplify it. Here your IDC, if you are considering the resistance, in that case Vm by, instead of pi, into RS plus RF plus RL. If you put all this and simplify it, you will get the percentage regulation, that is this percentage regulation value. It is depending upon the value of the resistance, so it will be RF plus RS by RL into 100%. So if you remember this RF plus RS by RL into 100%, directly the percentage regulation you can calculate. So it is basically depending upon the resistance, source resistance, secondary winding resistance, and load resistance and forward resistance of the diode. So basically based upon the diode resistance, all the resistance of the circuit, the percentage regulation will be calculated. And this percentage regulation is basically it is the shows the variation of your DC output voltage with respect to the DC output current. So you can calculate that. So these are the parameters whatever it is utilized for the evaluation or performance evaluation of the rectifier circuit, and any rectifier circuit, it may be half wave, full wave, or any rectifier. So as we have seen that this it is having a very poor performance, the half wave rectifier, that then we switch over towards the full wave rectifier. So this full wave rectifier circuit. So there are two types of full wave rectifier, as you know. One is your, have you studied this full wave rectifier circuit? One is called as your center tape full wave rectifier. Another is your bridge rectifier. So these two full wave rectifier we are going to study. So here the center tape full wave rectifier circuit means how it will work. The center tape full wave rectifier circuit, center tape full wave rectifier circuit. Okay, so in the center tape full wave rectifier circuit, whatever the transformer we are using, suppose this is the input voltage and this is the transformer. So in the center tape rectifier circuit, we will use two diode. Okay, instead of using one diode, here two diodes are used. Let's say D1 and D2 are two diodes, and this load is connected like this. Here the load is connected. This is the load. Okay, and this will be one end of the load is connected to the center point of this secondary winding. Okay, this is the primary winding, this is the secondary winding. So exactly at the center point, if you are connecting the connecting or we are tapping the center of that secondary winding, that is called the center tape rectifier. So what is the benefit of this center tape rectifier? Whatever the, suppose here we are applying the VI of input VI. Okay, let's say N1 is equal to N2. So whatever the VI we are getting here, giving here, so same VI amount should be in the secondary winding. So once you center tap this secondary winding, what will happen? The same input voltage, like in here, in this case, whatever the voltage across from this point to this point, and one voltage from this point to this point. So two VI we are getting here. So like suppose if you are giving the primary input in the primary voltage, suppose in the primary winding you are giving the input voltage like this. Okay, at the secondary, in the upper half, we are getting the voltage, like the same voltage will appear at the upper half, and in the lower half also we are getting the voltage, but in the opposite phase we are getting. That means if you are giving here, this is the same, let's say VI, which is applied at the primary winding, its peak is Vm. Okay, so here also Vi will appear, here also Vi will appear. Only the difference is that the opposite polarity of Vi is just the opposite polarity of Vi, or this Vi we are getting. Or rather, just don't get confused. Same, you just consider two VI will appear at this two side, upper half and lower half. So it is also VI, it is also VI. So let's analyze the circuit performance. So from 0 to, let's say pi, this is 2 pi. Okay, so when we are analyzing the circuit like from 0 to pi, so from 0 to pi positive voltage we are providing. So positive voltage when we are providing, this will be plus minus Vi, this will be plus minus Vi. So this positive terminal is making this D1 forward biased. So during the positive half cycle, that is from, if you are 0 to pi, for the positive half cycle, this is for analysis for the positive half cycle. For positive half cycle, your D1 becomes forward biased. Okay, D1 become forward biased. This positive terminal is making this D1 forward biased. And what is the condition of D2 now? So this is positive negative. So negative is applied to the P side of this D2. So D2 becomes reverse biased. So during the positive half cycle, one diode becomes forward biased, another diode becomes reverse biased. So your circuit will be like this. So forward bias will replace it by the short circuit equivalent, and here the load is there. And in the reverse bias, the diode is open circuit. So this is the D1 condition. This is the condition of D2. It is reverse biased open circuit. Okay. So here. Okay, so here BI, this is BI. Okay, this is the load resistance RL. So the current will flow through this circuit. So due to this BI, the current will flow from positive terminal to the negative terminal. So the direction of the current will be, here the direction of the current will be like from positive terminal the current will pass. Okay, this is the direction of the current. This is the open path, so the current will not enter into the open path. Open path means infinite resistance. So the current will move across this load in this path. Okay, so this is the direction of the current. So according to, if you follow the direction of the current, then the voltage drop across the load will be from positive to negative. So the current direction, so this is positive to negative V naught we are getting. Okay, so what will be the V naught if you apply the Kirchhoff's voltage law here? And what will be the voltage? Negative to positive, Vi plus Vi, and across the diode, let's assume that the diode is ideal one, so voltage drop is 0. So directly we'll take positive to negative minus V naught, that is equal to 0. So we'll get V naught equal to Vi. Okay, so the maximum of your output voltage will be Vm. So for this positive half cycle, we are getting the same output, that is Vi, whatever the Vi, so peak value will be Vm. This is V naught. Okay. Likewise for the next half cycle, if you consider the second half cycle, like this pi to 2 pi, if you consider pi to 2 pi, so from pi to 2 pi, if you analyze the circuit, so from pi to 2 pi, we are giving the negative, that is minus of Vm sin omega t. So negative polarity voltage we are applying. So the circuit condition will be like this. The circuit will be now like this. So this is minus plus Vi, this is minus plus Vi. This is the load. Okay, so this is the condition of the diode. So first of all, let us, if it is negative to positive Vi, so this diode is now in this place, whatever the diode is there, this is reverse biased. So now your D1 is reverse biased. So in case of reverse biased, we can just replace this as the open circuit terminal. So we can replace the diode. We can replace the diode as open circuit terminal. So D1 will be open circuited and your D2 will be as we have reversed the polarity, so the D2 will be forward biased. We are giving the positive polarity to this. So this will be negative to positive, negative to positive. This is also Vi, this is Vi. So this positive terminal of Vi, it is making the diode forward biased. So D2 is forward biased, D2 is forward biased, D1 is reverse biased, and we are calculating the output across this load. Okay, so what will be the direction of the current now? Just say, so in the this loop is open circuited, so there is no current across this open circuit. Now this loop is closed circuited, so from the positive to negative the current will move. So this is the direction of the current. So from the positive terminal to the negative terminal, the current will move. So the diode load across the load, the output voltage. Again, if you follow the direction of the current, this will be positive, this will be negative. So this will be V naught. So you just mark that. Here also, if you apply the KVL, then negative to if you apply the KVL, negative to positive plus VI, positive to negative minus V naught equal to 0. So this V naught equal to VI. So during the negative half cycle also we are getting the same amount of your input voltage VI. Okay. So here also the peak will be VM. So you just see that during the positive half cycle also the direction of the current through the load is same. Negative half cycle also in the same direction the current is flowing. So now your current become unidirectional. It is not entering into the opposite direction in the opposite half cycle of the applied signal. Okay. So we are getting the second in the second half cycle also from pi to 2 pi also the same VI amount we are getting. So this kind of waveform we are getting from the center tape full wave rectifier circuit. So here what will be the this is pi, this is 2 pi, this is 3 pi, this is 4 pi, like this. So can you say in the half wave rectifier circuit what was the time period? In that case time period was 2 pi. Okay, here what is the time period?
Pi.
Pi.
Pi. So time period is decreasing. As the time period is decreasing, the frequency also increasing. Okay, so for this particular waveform, again we can calculate all the parameters. Okay, only the difference will be here. Only the difference is that in that case we are taking the time period 2 pi. So we want 0 to 2 pi we are considering, and 1/2 we are considering 0. Okay, so here we have to consider this is 0 to pi. The cycle will be 0 to pi. So when we are taking the averaging factor, so 1 by pi you have to consider. In that case we are taking 1 by 2 pi. All other things will be same. So only according to that we have to evaluate the parameters. So this is the case of center tape full wave rectifier circuit. Okay. So in the center tape full wave rectifier we are getting we are increasing the efficiency, but there are certain difficulties, like it is very difficult to find the exact center of the secondary winding. If you have seen the physically, if you seen the transformer, windings will be very small, wires are there in the winding, and it is very high amount of number of turns is very higher. So for that winding, it is difficult to find the which one is the middle point or the center point of that winding. That is one difficulty. Okay, and another one difficulty is that in this case, if you consider the peak inverse voltage, okay, if you consider the peak inverse voltage for this case, means in the reverse bias condition, whatever the voltage across the reverse terminal, that is the PIV rating. So here if you calculate the PIV, so what will be the PIV? You can say, let's take the reverse bias condition, means for this part you just apply the KVL and find the PIV. So what will be the PIV?
If both the diodes are same, then it will be VM in both the cases. But if they both have different properties, I guess then they will have different P.
No, both the diode you have to consider same. Otherwise, the circuit in the waveform will be different. Na? The diode will are different. So, what will be the PIV rating of this diode?
VM, ma'am.
VM or
Ma'am, VM.
2VM? You just consider
2V.
2
VM,
VM.
VM.
It will be just think it. I am just saying the answer. You just analyze yourself. Otherwise, we will discuss it. There is no issue. But its PIV rating will be twice of VM, because in the previous case, in the half wave rectifier case, when we were considering the PIV, at that case output voltage was 0. Due to the reverse biasing the circuit, there is no current across the load and the output was 0. But in this case, when we are taking the reverse bias condition, due to the other part of the circuit, the output voltage is never 0 here. The output voltage is there. Already one output voltage, that is V0 is equal to Vi, is there here. Okay. So when you consider the reverse bias condition, so this in this KVL, this Vi will appear, V0 is also appear. That V0 means Vi will again appear. So the PIV will be twice of VM here.
Yes, ma'am.
Okay. Earlier case V0 को हम लोग 0 ले लेते थे, because there was no current there. But here, due to this path, current is flowing across the load. So voltage across this two terminal, if you measure, then this voltage along with this voltage, both the voltage will appear. So here the PIV will be, the peak inverse voltage will be twice of VM. That means whatever the diode we will choose, that PIV rating must be greater than equal to twice of VM. This is the requirement for the PIV rating. So in this case, the diode which you require should have a higher PIV rating as comparison to your half wave rectifier circuit. Okay. So these are two shortcomings of this rectifier, center tape rectifier. One is your transformer winding for finding the center point of the transformer. Another is the higher PIV rating diodes are required, which is a little bit costlier. Okay. So one more full wave rectifier circuit is there, which is your bridge rectifier circuit, So let us discuss this after completing both the rectifier, because in the full wave rectifier means in the center tape also whatever the waveform we are getting, same waveform we will get through the bridge rectifier. So after both the rectifier discussion, we will go to the parameters, because the parameters for full wave will be same. It may be for a center tape or bridge, it doesn't matter. So the parameters are same. So we will analyze or derive the parameters for full wave rectifier in a common waveform. So let us first complete the discussion of the rectifier. So this is about the center tape rectifier. Another is your bridge rectifier. Okay. So in the bridge rectifier, actually we use 4 diodes. Okay. In this type of connection we will use here. Like if this is the, we'll make the bridge circuit. Several bridge you have gone through in your physics, I think. Wheatstone bridge, Maxwell bridge, कुछ bridge था ना तुम लोग का physics में?
Yes, ma'am.
Yes, ma'am.
Yeah. So this is also a bridge structure we will consider. So we will consider the diode in this way. And here there are four points, 4 nodes are there. So the input will be provided through 2 nodes. This is the V. Yes? Yes? What happened? Is there any question? It's anyone, someone is asking something. So what happened? Okay, so let us continue. So this BI will be given through the transformer also we can consider. Okay, so this BI will be given through the transformer. You can use what transformer here. Okay. So this is the BI, and the output load will be connected across these two terminals. So the load will be connected across these two terminals. So either you can draw the load here. Okay, so one terminal will be grounded. So this will be the RL. Either you can make the circuit like this, or directly somewhere you connect here and load you just put it outside also. Okay, so whatever the feasible way you can use. So let's the diode is, this is your, let's say D1, let's say this is D2, let's say D3 and D4. Four diodes are used here. Okay, so as during the positive, as usual, if this is the input waveform, okay, 0, pi, 2 pi, 3 pi, this is the input waveform Vi. So 0 to pi, first let us consider 0 to pi, this is the positive half cycle, this positive half cycle. So during the positive half cycle, this is the positive, this is negative, plus minus Vi we are giving here for the positive half cycle. Okay, so this terminal of the diode is getting, this node is getting positive, this node is getting negative. Okay, so tell me what will be the condition of the diode, which diode is forward biased, which diode is reverse biased. Okay, so this, if you see that what D2 is getting positive voltage, P side of the D2 is getting positive voltage, and here N side of the D1 is connected to positive voltage. We can say D1 is reverse biased and D2 is forward biased. In the other condition, negative voltage here, negative, this node is getting negative voltage. So D4, P side of the D4 is negative, N side of D3 is negative. So D3 is, N side is getting negative, means D3 is forward biased and D4 is reverse biased. So this D1 and D4, these two are reverse biased, and this D2 and D3, these two are forward biased. So the circuit condition will like this. If you see the circuit, so the circuit is like this. So this is D2, this is forward biased. Okay, let's say this is the load RL. Okay, this is forward biased, this path is reverse bias. Okay, this is the reverse bias path. D3 is forward biased. Okay, so D3 is forward biased. So this is short circuited, this is the D3 forward biased, this is D2 forward biased, and D4 is again reverse biased. This is reverse biased. Okay, so this is the negative terminal. So this is the plus minus Vi. Okay, so what will be the direction of current and what will be the output voltage? What will be the output voltage? Let's say, so the from positive terminal to the negative terminal there will be a closed path here. Okay, so if you see, okay, so if you see the path of the current from positive terminal, the current will flow. Okay, so this is the direction it is taking. So it will take the direction. So from positive to terminal. So this path is open path. So the current will not flow through this path. Through this D2, the current is flowing. Again, it will not go to the reverse bias path. It will turn this way. Okay. Again, it is in this way to the negative terminal. Okay, so the across the RL, the direction of current is from this point, let's say this point to this point, let's say this is the point A, this is the point B. So from A to B the current is flowing, from A to B, if it is A, this is B, from A to B the current is flowing. So the accordingly the voltage across the load will be plus minus V naught. Okay, so tell me what will be the value of V naught if you apply the Kirchhoff's voltage law here. So negative to positive plus Vi. So this voltage drop across the diode we are considering 0 as we are considering ideal one. Okay, if it is silicon then 0.7 drop will be there. Okay, so for ideal case let's say it is 0. So here positive to negative minus V naught, again it will be 0. So V naught is equal to your Vi for the positive half cycle. Okay. Likewise, in the next half cycle, when you consider the next half cycle, just the difference is that in the negative half cycle, the your just the there is a difference of your, let's say for the negative half cycle, let's say different color will use for the negative half cycle. Okay, so for the negative half cycle, if you consider from pi to 2 pi, this is the condition for pi to 2 pi to pi. In this case, we are getting the output voltage, which is for the positive half cycle, we are getting the output voltage the same 0 to pi. This is Vi, this is the V naught. So this is the same Bm we are getting for the positive half cycle. Again pi to 2 pi we will consider. So negative, for the negative half cycle, if you consider this will be negative, this will be positive. So this terminal will negative, this terminal will positive. So just the opposite. So here this D4 and D1 become forward biased and this two diode becomes reverse biased. So the circuit condition will be like this. This is the condition. So this will be the forward biased path. Okay, this is the load and this is the again forward biased path. And these two paths are open circuited path. This is the path of D2 and D3, which is open by reverse biased. Okay, and this D1 and D4 are forward biased. Now this is D1 and D4 are forward biased. This is the load, and this is negative to positive Vi. So the current will move from this positive terminal to the negative terminal. So this is the direction of the current. This is the direction of the current. So across the load, we have to calculate the V naught, direction of V naught. So as the current is moving from this point, let's say this is A, this is the B. Again from A to B, the current is moving. So this is the positive, this is the negative. So the same amount of this Vi we are getting. So in the next half cycle also we are getting this same Vi. So in this way, the waveform will vary from both the half cycle. So same type of output waveform we are getting here. Okay, so for this case, can you calculate the PIV? What will be the PIV? What will be the PIV?
Greater than equal to 2m.
Vm, yes, PIV is Vm. So the PIV rating must be greater than equal to Vm. So here in the bridge rectifier circuit, there is no issue of center pointing, and low PIV rating diodes are required. One disadvantage is that 4 diodes are used here. Instead of 2 diodes, here 4 diodes are used here. But the less PIV rating is there, and also there is no requirement of center tapping of the rectifier, because in the previous case, if properly center tap is not done, then the waveform may be distorted. So this is about the full wave bridge rectifier circuit. Okay, so in the I'm just giving you as an assignment that you calculate the, for the full whatever the parameters we are calculating, that is VDC, IDC, then VRMS, IRMS, ripple factor, that is your gamma, then efficiency, that is eta. Okay, then form factor and transformer utilization factor. All these parameters you just calculate for this waveform, and only where just what is the difference, you know, in that case pi to 2 pi was 0, but here you have to consider the cycle as the 0 to pi, because here the time period becomes pi only. After this, after this much again the cycle is repeating, so here the periods is 0 to pi, so only the integration limit will change, rest part will be same. So considering that, you just calculate all these parameters. Otherwise, if you are not able to calculate, then we will discuss. I hope okay, all of you will are very much acquainted with your integration derivative. Just recently you have appeared the J, so you obviously are very much expert in that area. So I hope okay, all the values you just calculate, and we will verify it in the next class. If it is not somebody is not getting that how to calculate, then we will do, otherwise we will switch over towards the Zener diode, so that if you get time, then so we will discuss some numericals also. Okay.
Ma'am, how many questions will be asked in the quiz?
Till now we have not commonly decided, because I think DK Upadhyay sir is making the question. After that we will discuss. So it may be 10 or 20. It is till now it is not decided.
Ma'am,
And the quiz is on 2nd of Feb.
Yeah, 2nd of Feb from 6 to 6:30.
Don't you think we should get a bit more time, because I guess on day our course will end and we have to give it on Tuesday or Thursday, Tuesday or Wednesday.
It is a 10 marks quiz, and content is not much more. And these are many things you know from your 12th only. So there is no issue.
ma'am, actually I had a doubt.
Yes.
Ma'am, yesterday you taught us about the RMS value of the pure AC component.
Okay.
Can you once again please just explain it? What does it mean? Because you explained it through the Fourier series, but ma'am,
Yes.
physically, what does it mean through the graphs that we are drawn across the load?
Okay. If do you have time? I think it is only 10 o'clock. So so those who are having the class, you can leave. I have taken the attendance. You have to join other class also, na?
Yes, ma'am.
So we can discuss it little bit more in the next class, and also I will make a graphical representation also, so that it will be more clear.
Yes,
Okay.
ma'am. Yes, ma'am.
Okay. So in the next class I will provide that.
Okay, thank you, ma'am.
Okay.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Thank you, ma'am.